Introduction to NVA Microsegmentation. Welcome to our comprehensive deep dive into network virtual appliances and microsegmentation in Google Cloud Platform. This content is absolutely critical for the GCP Network Professional Certification Exam. Please consider subscribing to the channel. I produce videos daily on AWS, Azure, and GCP. Hit the notification bell as well to get notified. Thank you in advance for your subscription. Today we're going to explore how to insert third-party security appliances into your GCP network traffic flow. This enables advanced security controls that go far beyond what native VPC firewall rules can provide. Think about this scenario. You're working for a financial services company that needs to meet strict PCI DSS compliance requirements. They need deep packet inspection, advanced threat detection, and detailed logging that only commercial security appliances can provide. GCP's native firewall rules, while powerful, operate at layer 3 and 4. They can't do application layer inspection or content filtering. We'll cover everything from the fundamental concepts to advanced implementation patterns, including east-west traffic inspection, which is crucial for zero-trust architectures. The patterns we discuss today are used by major enterprises to secure their cloud infrastructure. By the end of this session, you'll understand how to architect scalable, highly available NVA deployments that can handle production workloads while maintaining security and compliance requirements. What are network virtual appliances? Network virtual appliances are specialized virtual machines that perform network functions traditionally handled by physical hardware appliances in data centers. These include firewalls, intrusion prevention systems, load balancers, VPN concentrators, and WAN optimization devices. The key difference from native GCP services is that NVAs run as customer-managed virtual machines. This gives you complete control over the configuration and policies, but also means you're responsible for their operation, scaling, and maintenance. Let me give you a real-world example. Imagine you're migrating from an on-premises environment where you have Palo Alto firewalls doing advanced threat prevention. You want to maintain the same security policies and logging formats in the cloud. While GCP has CloudArmor for DDoS protection and VPC firewall rules for basic filtering, you need the advanced features of your existing Palo Alto investment. The challenge is making sure traffic actually flows through these appliances. Unlike physical networks where you can place a firewall in the network path, in cloud environments, you need to use routing to steer traffic through your NVAs. This is where custom routes become critical. They override the default VPC routing behavior to ensure traffic goes where you want it to go. Without proper routing configuration, traffic will bypass your expensive security appliances completely. Custom routes in GCP VPC networks have an implicit routing table that handles basic connectivity. Every VPC automatically gets routes for its subnets, a default route to the Internet gateway, and routes for any peered networks. This works great for simple connectivity, but does not give us the control we need for NVA insertion. Custom routes allow us to override this default behavior. We have two main approaches: static routes and policy-based routes. Let me explain the critical differences because this often comes up on the exam. Static routes are simple. They manually define where traffic with specific destination should go. You specify a destination CIDR block and point it to a specific virtual machine instance. The problem is that if that virtual machine fails, your traffic fails too. There is no automatic failover, no load balancing, and no health checking. Policy-based routes with internal load balancers are the recommended approach for production deployments. Instead of pointing to a single virtual machine, you point to an internal load balancer that fronts a pool of NVA instances. This gives you high availability, automatic scaling through managed instance groups, and most importantly, symmetric routing. Symmetric routing is crucial for stateful appliances like firewalls. The same NVA instance that processes the outbound packet must also process the return packet, otherwise the firewall's state table gets confused and drops the traffic. This distinction between static routes and policy-based routes is a key exam topic. Remember, static routes for simple scenarios and testing, policy-based routes with ILB for production deployments. Static routes implementation. Let's walk through a basic static route implementation to understand the mechanics. The G-Cloud Compute Routes Create command is what we use to manually define routing behavior. The network parameter specifies which VPC this route applies to. Routes are VPC specific, so if you have multiple VPCs, you need to create routes in each one. The destination range parameter is the CIDR block this route applies to. Using quad 0 means this route applies to all internet-bound traffic, essentially creating a default route. This is common for egress inspection scenarios where you want all outbound traffic to go through your NVA. The next hop instance parameter points to your NVA virtual machine. This has to be the exact instance name, and you also need to specify the zone with the next hop instance zone parameter. This tight coupling to a specific instance is one of the limitations of static routes. The priority parameter is crucial for understanding GCP routing. Lower numbers mean higher priority. The default internet route in GCP has priority 1000, so by setting our priority to 800, we ensure our custom route takes precedence. This creates a routing table entry that essentially says for any traffic destined to the internet, send it to this specific NVA instance instead of the default gateway. The NVA then inspects the traffic and forwards it to its final destination. But remember the limitations: no high availability, no load balancing, and potential for asymmetric routing if you have multiple routes or complex network topologies. Policy-based routes with ILB architecture. This diagram shows the recommended architecture for production NVA deployments using policy-based routes with an internal load balancer. Let me walk you through why this architecture is so much better than static routes. First, instead of routing to a single NVA instance, we route to an internal load balancer. The ILB acts as a single, stable endpoint that distributes traffic across multiple NVA instances in a managed instance group. The managed instance group provides automatic scaling based on CPU utilization, network throughput, or custom metrics. If traffic increases, new NVA instances are automatically created. If instances fail health checks, they're automatically replaced. The internal load balancer uses a health check to monitor the NVA instances. Only healthy instances receive traffic. If an instance becomes unhealthy, maybe the NVA software crashed or the virtual machine is overloaded, the ILB stops sending traffic to it until it recovers. Most importantly, the ILB maintains session affinity. This means that both directions of a network conversation, the initial request and the response, are handled by the same NVA instance. This is critical for stateful security appliances that maintain connection state tables. The VPC peering connection allows the application VPC to communicate with the security VPC where the NVAs are deployed. This creates a hub and spoke topology where the security VPC acts as the central inspection point. From a routing perspective, you create a policy-based route that points to the ILB's forwarding rule rather than individual instances. This gives you a single, highly available next hop that automatically handles the complexity of load balancing and failover. The hub and spoke model is the most common and recommended pattern for NVA deployment in enterprise cloud environments. Let me explain why this architecture is so powerful and how it maps to real-world requirements. In this model, you have a dedicated security VPC that acts as the hub. This VPC contains all your shared security services, not just NVAs, but potentially also shared services like DNS resolvers, logging endpoints, or monitoring systems. Your application VPCs are the spokes. These contain your actual workloads, web servers, databases, application servers. Each spoke VPC peers with the hub security VPC, creating a star topology. The magic happens in the routing configuration. By creating custom routes in the spoke VPCs, you can force specific traffic flows to go through the hub for inspection. For example, all internet-bound traffic from the production VPC routes through the NVAs in the hub before reaching the internet. This architecture provides several critical benefits. First, it centralizes security policy enforcement. Instead of having security appliances in every VPC, you have a single security stack that all traffic flows through. This reduces costs and management overhead. Second, it provides consistent security posture across all your applications. Whether you have a development environment, production environment, or DMZ, they all get the same level of security inspection. Third, it enables efficient resource utilization. A single pool of NVA instances can handle traffic from multiple application environments, with automatic scaling based on overall demand. From a compliance perspective, this model makes auditing much easier. You have a single point where all traffic inspection happens, making it easier to demonstrate to auditors that all required security controls are in place. Traffic steering patterns explained. Understanding different traffic patterns and how to steer them through NVAs is fundamental to designing effective security architectures. Let me break down the key patterns you'll encounter in real-world deployments. North-south traffic refers to communication that crosses the network perimeter, either inbound from the internet to your applications, or outbound from your applications to the internet. This is the traditional focus of network security. For north-south ingress, traffic comes from the internet through an external load balancer, then to your NVA internal load balancer for inspection, and finally to your application instances. This pattern is common for web applications that need WAF functionality or DDoS protection. For north-south egress, traffic from your applications is routed through the NVA using a default route, Quad 0, then forwarded to Cloud NAT or a NAT gateway for internet access. This is critical for data loss prevention and monitoring outbound communications. East-west traffic is communication within your network infrastructure. This includes traffic between different VPCs, between different subnets within the same VPC, or between different application tiers. East-west inspection is increasingly important as organizations adopt zero-trust security models. The traditional perimeter security approach assumed that internal traffic was trusted, but modern threats often involve lateral movement within the network. For spoke-to-spoke communication, you create routes in each spoke VPC that direct traffic destined for other spokes through the hub NVA infrastructure. For intra-VPC communication, you use more granular routes or policy-based routes to inspect traffic between specific subnets or application tiers. The key is understanding that each pattern requires different routing strategies and has different performance and security implications. NVA Infrastructure Setup Foundation. Let's walk through the actual implementation, starting with building the foundational infrastructure. Every parameter here is important for the exam and for real-world deployments. We start by creating a dedicated security VPC with subnet mode custom. Custom mode gives us complete control over IP address ranges, which is crucial for complex network architectures. The alternative, auto mode, automatically creates subnets in every region, which wastes IP space and reduces control. The NVA subnet gets a /24 network, which provides 254 usable IP addresses. This might seem like overkill for a few NVA instances, but remember that we need IPs for the load balancer, health checks, and potential future expansion. The instance template is where we configure our NVA virtual machines. The CAN-IP forward flag is absolutely critical. This tells GCP to allow this virtual machine to forward packets that aren't destined for its own IP address. Without this, the virtual machine can receive traffic but can't forward it to other destinations. The machine type N1 Standard 4 provides 4 volts CPUs and 15 GB of RAM. This is usually adequate for medium throughput scenarios, but you'll need to size based on your actual traffic patterns. Network appliances are often CPU intensive due to packet processing overhead. The startup script enables IP forwarding at the OS level using sysctl. Both GCP level forwarding and OS level forwarding must be enabled. The script also sets net.ipv4.ip_forward equals 1 permanently in /etc/sysctl.conference. The tags parameter is used for targeting firewall rules. This lets us create firewall rules that apply only to NVA instances, not to other virtual machines in the VPC. Internal Load Balancer Configuration Deep Dive. The internal load balancer configuration is the heart of a scalable NVIDIA deployment. Let me explain each component and why it's configured this way. The Managed Instance Group creates and manages a pool of identical NVIDIA instances based on our template. Starting with size gives us immediate redundancy. The MIG can automatically scale this based on demand, but having at least 2 instances ensures high availability even during maintenance or failures. The health check configuration is critical for reliable operation. We use TCP health checks on port 22, SSH, because it's a basic connectivity test that works with most virtual machine images. In production, you might use a more sophisticated health check that actually tests the NVIDIA functionality. The check interval means the health check runs every 10 seconds. The timeout gives each individual check 5 seconds to complete. The healthy threshold means an instance must pass 2 consecutive health checks to be considered healthy, while unhealthy threshold means it must fail 3 consecutive checks to be marked unhealthy. These thresholds prevent flapping, instances rapidly switching between healthy and unhealthy states due to temporary network issues or brief CPU spikes. The backend service uses load balancing scheme, which means this load balancer is only accessible from within the VPC, not from the internet. The protocol setting allows the load balancer to handle any TCP traffic, regardless of the application protocol. When we add the MIG to the backend service, we're telling the load balancer which instances should receive traffic. The load balancer continuously monitors the health of these instances and only sends traffic to healthy ones. The forwarding rule creates the actual load balancer endpoint, the IP address that routes will point to as their next hop. VPC peering setup and routing implications. VPC peering is how we connect our hub security VPC with the spoke application VPCs. Understanding peering mechanics is crucial for both the exam and real-world implementations. Each peering relationship is bidirectional but must be established from both sides. When we create hub-to-prod peering, we also need to create prod-to-hub peering. Until both sides are configured, the peering won't work. The auto-create routes flag automatically creates routes in each VPC's routing table for the peers subnets. For example, when we peer the hub VPC 10.0.0.0 with the production VPC 10.1.0.0, each VPC automatically gets a route to the other's IP space. However, these automatic routes have priority, the same as default routes. This means we can override them with custom routes that have higher priority lower numbers to force traffic through our NVAs instead of direct peering. The subnet IP ranges are carefully planned to avoid overlap. The hub uses 10.0.0.0. Production uses 10.1.0.0, development uses 10.2.0.0, and data uses 10.3.0.0. This planning is essential because VPC peering doesn't work with overlapping IP ranges. Regional subnets in US Central 1 provide high availability within that region. If you need multi-region deployment, you create additional subnets in other regions. The peering relationships create the foundation for our hub and spoke topology, but the real magic happens when we add custom routes that override the automatic peering routes to force traffic through our NVIDIA infrastructure. One important limitation to remember: VPC peering is not transitive. If VPCA peers with VPCB, and VPCB peers with VPCC, VPCA cannot directly communicate with VPCC through VPCB for spoke-to-spoke communication. Traffic must be explicitly route-ed through the hub. Understanding East-West Traffic Inspection. East-West traffic inspection represents a fundamental shift in network security thinking. Traditional perimeter security models assumed that once traffic was inside your network, it was trustworthy. This assumption has proven dangerous in modern threat landscapes. Let me give you a real-world scenario. Imagine an attacker compromises a web server in your DMZ through a vulnerability. With traditional perimeter security, that attacker could potentially move laterally to access your database servers, internal APIs, or other sensitive systems without any additional inspection. East-West traffic inspection addresses this by treating every network segment as potentially compromised. It's a core principle of zero-trust architectures: never trust, always verify, even for internal communications. We distinguish between different types of east-west traffic: spoke-to-spoke communication between different VPCs, intra-VPC communication between subnets, and service-to-service communication between application tiers. Each has different security implications and performance considerations. The key insight is that lateral movement, an attacker's ability to move from one compromised system to another, is often more damaging than the initial breach. By inspecting east-west traffic, we can detect and prevent this lateral movement, significantly reducing the blast radius of security incidents. From a compliance perspective, many frameworks now require comprehensive traffic monitoring. NIST, PCI DSS, and other standards are moving toward requiring inspection of all network communications, not just perimeter traffic. Spoke-to-spoke communication architecture. This diagram illustrates how spoke-to-spoke communication flows through our centralized NVA infrastructure in the hub. Let me walk you through the traffic flow and explain why each component is critical. When a web server in the production VPC needs to communicate with a database in the data VPC, the traffic doesn't flow directly through the VPC peering connection. Instead, our custom routes force it through the hub's NVA infrastructure. The color coding helps visualize the different VPC environments. Production is shown in blue, development in green, and data in orange. The hub security VPC in yellow acts as the central inspection point. Notice how the NVA internal load balancer distributes traffic across multiple NVA instances. This provides high availability and load distribution. If one NVA instance fails or becomes overloaded, traffic automatically flows to healthy instances. The session affinity configuration in the ILB ensures that both directions of a conversation, the initial request from prod to data, and the response from data back to prod, flow through the same NVA instance. This is crucial for stateful inspection. From a performance perspective, this architecture adds one additional network hop compared to direct VPC peering. However, the security benefits typically outweigh this minimal latency increase, especially for critical business applications. This pattern scales well because the NVA infrastructure is shared across all spoke VPCs. You're not duplicating security appliances in every environment. You're leveraging a centralized, highly available security service. Custom routes for east-west traffic implementation. Now let's implement the actual routing configuration that makes spoke-to-spoke traffic flow through our NVAs. Each command here is carefully crafted to override the automatic VPC peering routes. First, we capture the ILB IP address using a G-Cloud command with format output. This IP address becomes our next hop for all the custom routes we're about to create. The command substitution syntax executes the inner command and uses its output as a variable. The route from production to development VPC uses destination range 10.2.0.0/16, which covers all subnets in the development VPC. This is more efficient than creating separate routes for each subnet. The priority 100 setting is crucial. VPC peering automatically creates routes with priority 1000. Our custom routes with priority 100 will override these automatic routes, forcing traffic through our NVAs instead of direct peering. We need to create routes in both directions, prod to dev and dev to prod, to ensure symmetric routing. If we only created the prod to dev route, the initial request would go through the NVA, but the response would take the direct peering path, breaking stateful inspection. The same pattern applies to all other spoke-to-spoke combinations, prod to data, dev to data, and their reverse routes. This creates a full mesh of inspected communication paths. In production environments, you might want to be more selective about which traffic gets inspected. For example, you might only route database traffic or API calls through the NVAs, allowing less sensitive traffic to use direct peering for better performance. Policy-based routes offer much more granular control than simple destination-based routing. Instead of routing all traffic to a destination, you can target specific protocols, ports, or even source-destination combinations. The first example shows routing only MySQL traffic through the NVA. The SRC range covers the entire production VPC, but DEST range targets only the database subnet. Most importantly, protocols equals TCP and DEST ports equals mean only MySQL database connections get inspected. This selective approach has several benefits. First, it reduces the load on your NVA infrastructure since only critical traffic flows through it. Second, it minimizes performance impact on less sensitive communications. Third, it reduces licensing costs for throughput-based NVA licensing models. The next hop ILB URL parameter uses the full resource URL format. This is different from the next hop address we used in simple routes. The ILB URL format provides better integration with GCP's load balancing infrastructure and enables advanced features like health checking. The second example targets HTTPS traffic between web and application tiers. This is common in microservices architectures where you want to inspect API calls but allow other internal communications to flow directly. You can also use policy-based routes for more complex scenarios like routing traffic based on time of day, source IP ranges for specific user groups, or even custom headers in HTTP traffic. This flexibility makes PBR the preferred approach for sophisticated security architectures. From an exam perspective, remember that policy-based routes require regional internal load balancers and are more complex to manage than simple static routes, but they provide much more flexibility and granular control. Intra-VPC microsegmentation deep dive. Intra-VPC microsegmentation is more complex than spoke-to-spoke inspection because GCP's default behavior allows direct communication between subnets within the same VPC. We need to override this default behavior using tagged routes and dedicated NVA infrastructure. The approach here is to deploy NVA infrastructure directly within the production VPC rather than relying on a separate hub VPC. This reduces latency for intra-VPC communications but requires more careful planning to avoid IP conflicts. The prod NVA subnet gets its own IP range 10.1.100.0 that doesn't conflict with the existing web and app subnets. This subnet hosts the NVA instances and the internal load balancer that serves as the inspection point. The key innovation here is using route tags. The tags web servers parameter means this route only applies to instances that have the web server's network tag. This allows us to selectively apply microsegmentation rules to specific instance groups. For example, web servers get routes that force their app tier communications through the NVA, but database servers might have different routing rules or no special routing at all. This granular control is essential for performance optimization. The tag-based approach also simplifies management. When you deploy new web servers, you just apply the appropriate network tags, and they automatically inherit the correct routing behavior. No need to update routing tables manually. This pattern is particularly useful for compliance scenarios where you need to demonstrate that specific types of communications are always inspected, while other communications can remain uninspected for performance reasons. Firewall rules for NVIDIA access, critical configuration. Firewall rules for NVIDIA deployments are often overlooked, but are absolutely critical for proper operation. Without the right firewall configuration, your carefully planned routing will fail because traffic cannot actually reach the NVAs. The allow-NVIDIA-ingress rule permits traffic from all spoke VPC IP ranges to reach the NVA instances. The rule's parameter, specifying TCP, UDP, and ICMP, covers all major protocols. In production, you might want to be more restrictive, but for initial deployment, this broad rule ensures connectivity. The target tag's parameter set to NVIDIA-instance is crucial. It means this rule only applies to instances with that specific tag. This prevents accidentally opening up other instances in the security VPC to traffic from the spoke VPCs. The allow-NVIDIA-egress rule is equally important. It allows the NVAs to forward traffic to their final destinations. Without this rule, traffic would reach the NVAs but could not be forwarded onward, effectively creating a black hole. The health check rule is absolutely critical and often forgotten. GCP's load balancer health checks originate from specific IP ranges: 35.191.0.0 and 130.211.0.0. If these ranges cannot reach your NVA instances, the load balancer will mark all instances as unhealthy and stop routing traffic to them. I have seen production deployments fail because teams forgot the health check firewall rule. Everything looks correct in the routing configuration, but traffic does not flow because the load balancer thinks all NVAs are down. In some environments, you might also need rules for NVIDIA management traffic. For example, SSH access for administration, HTTPS for web-based management interfaces, or SNMP for monitoring. Plan these carefully to maintain security while enabling necessary operational access. Monitoring and troubleshooting east-west traffic. Monitoring and troubleshooting NVIDIA deployments requires multiple layers of visibility. VPC's flow logs are your primary tool for understanding whether traffic is actually flowing through your NVAs as intended. The flow log configuration shows aggressive sampling settings, 100% sampling and 5-second aggregation intervals. This is expensive in terms of storage costs, but provides comprehensive visibility during initial deployment and troubleshooting phases. The logging metadata include _all metadata parameter captures source/destination VPCs, instance information, and geographic data. This metadata is crucial for understanding complex traffic patterns in multi-VPCs environments. The SSH traceroute command is a simple but effective validation tool. When you run traceroute from a web server to an app server, you should see the NVA's IP address as an intermediate hop. If you don't see it, your routing configuration isn't working correctly. The gcloud logging read command shows how to query flow logs to find specific traffic patterns. This query looks for traffic between specific source and destination IPs, which helps verify that your routing rules are working as expected. The backend service health check command is critical for NVIDIA troubleshooting. If instances show as unhealthy, traffic won't flow to them regardless of your routing configuration. Common causes include firewall rules blocking health checks or NVIDIA software not responding properly. In production environments, you should also monitor NVIDIA performance metrics, CPU utilization, network throughput, session counts, and application-specific metrics like firewall rule hits or threat detections. Set up alerting for both infrastructure health and security events. Network Intelligence Center provides additional visibility with topology visualization and connectivity testing. Use these tools to validate your network architecture and troubleshoot connectivity issues. Best practices for production NVIDIA deployments. Let me share the key best practices that separate successful production NVIDIA deployments from failed proof of concepts. These practices come from real-world experience with enterprise-scale deployments. ROT priority is fundamental to understanding GCP routing behavior. Custom ROTs with priority 100 will always override VPC peering ROTs with priority 1000. Default Internet ROTs also have priority 1000, so your custom ROTs take precedence. Use priorities strategically to create routing hierarchies. Symmetric routing is critical for stateful security appliances. Firewalls, IPS systems, and load balancers maintain state tables that track connection information. If outbound traffic goes through NVIDIA Instance 1 but return traffic goes through NVIDIA Instance 2, the state tables won't match and traffic gets dropped. The internal load balancer's session affinity feature solves this by ensuring both directions of a conversation use the same backend instance. Configure this properly or your stateful appliances will behave erratically. IP forwarding must be enabled at both the GCP level CAN-IP forward and the operating system level NET IPv4 IP_forward. Forgetting either one will prevent the NVA from forwarding traffic, even though it can receive it. Performance considerations are crucial for east-west traffic because it's often high volume, low latency communication between application tiers. Use selective inspection with policy-based routes to minimize performance impact on non-critical traffic flows. Consider NVIDIA licensing models carefully. Many commercial appliances charge based on throughput, number of sessions, or features enabled. East-west inspection can dramatically increase your licensing costs if not planned properly. Plan for failure scenarios. What happens if the NVA instances fail? If the load balancer fails? If the entire security VPC becomes unavailable? Design fallback mechanisms and test them regularly. GCP Network Professional Exam Focus Areas. For the GCP Network Professional Exam, certain NVIDIA concepts appear frequently and in specific contexts. Let me highlight the key areas you need to master. The exam loves to test the difference between static ROTs and policy-based ROTs. Remember, static ROTs for simple scenarios and testing, policy-based ROTs with ILB for production deployments that require HA, scalability, and symmetric routing. Hub and spoke architecture questions are common. Understand why centralized security VPCs are preferred. Cost efficiency, consistent policy enforcement, simplified management, and scalability. Be able to explain the trade-offs between hub and spoke and distributed security models. East-west versus north-south traffic distinction is crucial. North-south is perimeter traffic internet ingress/egress. East-west is internal traffic VPC to VPC, subnet to subnet. Each requires different routing strategies and has different performance implications. Symmetric routing questions often involve stateful appliances. Understand why it matters, how session affinity solves it, and what happens when it breaks. This concept appears in many different question formats. ROT priority calculations come up frequently. Remember that lower numbers mean higher priority. Custom ROTs typically 1000 override VPC peering ROTs 1000 and default ROTs 1000. Know how to design routing hierarchies using priorities. Performance and cost considerations are increasingly important in exam questions. Understand the trade-offs between comprehensive inspection and network performance. Know when to use selective inspection versus blanket traffic steering. Integration with other GCP services appears in complex scenarios. How do NVAs interact with CloudArmor, VPC service controls, private Google Access, and CloudNet? Understand the interaction patterns and limitations. Course summary and next steps. We've covered comprehensive NVIDIA microsegmentation strategies for Google Cloud Platform, progressing from fundamental concepts to advanced production deployment patterns. This knowledge directly applies to both the GCP Network Professional Exam and real-world enterprise implementations. The foundation we built starts with understanding why NVAs are necessary, providing advanced security capabilities that native GCP services can't deliver. We explored the critical differences between static routes and policy-based routes, emphasizing why ILB-backed routing is essential for production deployments. The hub-and-spoke architecture pattern provides the scalability and operational efficiency needed for enterprise environments. By centralizing security services in a dedicated VPC, organizations can achieve consistent security posture across all applications while optimizing resource utilization. East-West traffic inspection represents the evolution toward zero-trust architectures. By inspecting internal communications, organizations can detect and prevent lateral movement, significantly reducing the impact of security breaches. The implementation details we covered, from infrastructure setup through monitoring and troubleshooting, provide the practical knowledge needed to deploy these patterns successfully in production environments. For your next steps, I recommend implementing these patterns in your own GCP lab environment. Start with the basic hub and spoke setup, then add complexity with east-west inspection and policy-based routing. Practice troubleshooting scenarios because that's where deep understanding develops. Explore different NVA solutions to understand their capabilities and limitations. Each vendor has different strengths. Some excel at threat prevention, others at application visibility, still others at performance. Most importantly, understand that network security is evolving rapidly. The patterns we've discussed today represent current best practices, but continue learning as new threats emerge and new capabilities become available.